When Voyager 1 crossed the invisible edge of our solar system, its instruments picked up on something odd. Out beyond the heliosphere, the space around the spacecraft actually seemed to get denser. Specifically, the plasma density, the concentration of charged particles outside the sun's protective bubble, was climbing. 6 years later, its twin, Voyager 2, confirmed the same thing. Right now, both machines are pushing further into the space between the stars, and their journey is going to last so long that they'll outlast not just the people who built them, but quite possibly the stars we see in the sky tonight. There's one part of this story I still can't quite get my head around, though. How are we still hearing from them? How do two spacecraft built half a century ago, now tens of billions of kilometers from Earth, still manage to send us data about these anomalies in real time right now? The story of these probes starts with a rare cosmic coincidence. Back in the mid-1960s, a student at NASA's Jet Propulsion Laboratory, while working through orbital mechanics, stumbled onto something remarkable. In the late 1970s, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, were going to line up in just the right way. What made this so special is that planets travel around the sun at different speeds, so an alignment like this only comes around once every 176 years. Before that window, we simply didn't have the technology to make the trip. And once the planets drifted apart again, that was it. A true now or never opportunity. Here's the thing about traveling in space: you can't just fly in a straight line the way we do on Earth. Everything out there is moving in curved paths, constantly tugged by gravity. To reach a distant planet, a spacecraft can't just point forward and go, it has to keep adjusting its path. And that takes an enormous amount of energy. At the time, humanity didn't have rockets that could carry enough fuel for a direct shot at Neptune. Flying there the normal way would have taken a punishing 30 years. But that rare planetary alignment made something called a gravity assist possible. Think of it like a slingshot, except instead of an actual sling, the spacecraft gets caught by the invisible pull of a planet's gravity. As the planet moves along its orbit, its gravity grabs the incoming probe, drags it along for a bit, hands over a slice of its own orbital energy, and then flings the probe onward with a huge, essentially free boost of speed. That trick cut the travel time from 30 years down to just 12. NASA wasn't about to leave this to chance, so they built two identical probes with heavy redundancy. Backup computers, backup thrusters, dual communication systems, the works. Voyager 2 actually launched first, in August 1977, on a longer, slower path designed to swing by all four planets. Voyager 1 followed 16 days later on a faster, more direct route. Its job was to catch up with its twin and take a close look at the biggest moons of Jupiter and Saturn. Thanks to its higher speed, it pulled ahead of Voyager 2 even before reaching Jupiter. What it sent back changed science forever. Researchers were expecting to see a dead, boring rock. Instead, Jupiter greeted them with violent, churning turbulence. Voyager 1 captured a series of images that scientists back on Earth stitched together into a time-lapse, and for the first time, people could see that Jupiter's atmosphere wasn't some static painting. It was a living system of jet streams, swirling storms, and vortices. On its moon Io, astronomers spotted active volcanoes spewing bluish plumes into space. Next up was Saturn, with its sprawling system of hundreds of rings. This is where the twins' paths split apart, and that was very much by design. Voyager 1 was sent close to Titan, the only moon we know of with a thick atmosphere. Titan's gravity was strong enough to sharply bend the probe's course, flinging it up out of the plane of the planets and off into deep space, which meant giving up any shot at visiting the other outer worlds. Voyager 2, meanwhile, kept going on what's now called the Grand Tour, becoming the only spacecraft ever to visit both ice giants. When it reached Uranus, the probe found something genuinely bizarre. Not only does Uranus spin on its side as it orbits the Sun, but its magnetic field is tilted a whopping 59 degrees from its axis of rotation, and the center of that field isn't even lined up with the planet's core. For comparison, Earth's magnetic field behaves roughly like a giant bar magnet, tilted only about 11 degrees from our spin axis, with its source sitting deep inside the planet. Uranus is just weirder. Its magnetic axis is skewed almost 59 degrees and badly off-center. So as the planet rotates, its magnetic shield doesn't spin smoothly at all, it wobbles wildly through space. From there, the probe pushed on to Neptune, where it clocked the fastest winds anywhere in the solar system, up to 2,400 kilometers per hour. If you tried to picture wind speeds like that here on Earth, we're talking supersonic gusts. They wouldn't just rip roofs off houses, they'd tear through buildings, cars, entire neighborhoods, like a hurricane so extreme we don't even have a category for it. After Neptune, Voyager 2's cameras were switched off. Voyager 1's followed in 1990, right after it captured the now famous pale blue dot photo. There were no more nearby worlds left to photograph, and every watt of power had become too precious to spend on imaging. From that point on, the real value of these probes shifted to their other instruments: particle detectors, magnetometers, plasma sensors, the tools built to sense invisible radiation and magnetic fields, feeding back data that no telescope could ever hope to capture. So the cameras are off. The spacecraft are drifting through the cold void between stars, and yet, here's the paradox. Nearly 50 years later, priceless scientific data from the edge of the solar system is still making its way back to us. Which brings us right back to the big question: how are we even hearing them? To really appreciate what's going on, you need to look at the hardware itself. All 6 onboard computers on each Voyager combined have a total of just 68 kilobytes of memory. That's less than the chip inside a modern car key fob. The phone sitting in your pocket right now is millions of times more powerful than the entire flight system running these spacecraft. And all the data gets recorded onto a vintage 8-track digital tape recorder. The kind of tech you'd expect to find behind glass in a museum, but the wildest part is the communication system. Each spacecraft beams its data home using a transmitter that puts out roughly 20 watts of power, about what you'd get from the little bulb inside your fridge. The Voyagers are now more than 24 billion kilometers away, and even traveling at the speed of light, a radio signal takes over 22 hours just to cross that distance. Over such an enormous stretch, the signal spreads out across a massive area, and only a tiny sliver of the original transmission ever actually reaches Earth. By the time it arrives, the signal's power has dropped to a fraction of an attowatt, a unit I'd honestly never even heard of before researching this. Less than 1/1000th of a watt. It's such a faint whisper of radio noise that without enormous antennas it would simply vanish into the background static of the universe. So how do you even pull a signal that weak out of the roar of deep space? The answer is all here on Earth. NASA relies on the Deep Space Network, 3 sites built around massive 70-meter radio dishes located in the deserts of California, Spain, and Australia. They're spaced out so that as Earth spins, there's always at least one dish pointed toward the distant probes. These giant dishes gather up the incoming radio waves across their huge surface area and focus them down to a single point. The problem is, a dish that big picks up everything: radiation from distant galaxies, noise from Earth's own airwaves, even electronic noise generated internally. So how do engineers isolate one impossibly faint signal out of all that chaos? It comes down to a 3-stage filtering process. First, they have to strip out interference from Earth itself. Cell towers, radar, satellites. That's exactly why the Deep Space Network sites sit out in remote deserts far from civilization and operate on carefully reserved radio frequencies. Second, they need to filter out noise from other stars and galaxies. The 70-meter dish is extremely directional, so it locks onto one tiny, precisely calculated patch of sky and ignores everything else. On top of that, engineers know the exact baseline frequency Voyager broadcasts on, but because the spacecraft is moving so fast, that frequency keeps shifting. This is the Doppler effect in action. Think about an ambulance siren. As it races toward you, the pitch sounds high, and the instant it passes and speeds away, the pitch drops. That happens because a moving source compresses or stretches the waves it's emitting. Since Voyager is racing away from Earth, its radio waves get stretched out, and the frequency shifts lower. NASA's computers calculate that shift in real time and tune the receivers on the ground to match it, filtering out everything else in the process. Then there's a third problem, and it's a sneaky one: heat. Even the receiver's own hardware generates noise, because electrons jostling around inside the metal create a background hum. Left alone, that internal noise would completely swamp Voyager's already faint signal. To get around this, the most sensitive parts of the receiver are chilled down to nearly absolute zero, which suppresses that internal noise and lets engineers pick out a signal weaker than almost anything else around it. Absolute zero, by the way, is minus 273 degrees Celsius, the coldest anything can theoretically get, where the random motion of particles is reduced to almost nothing. It's only by combining geographic isolation, pinpoint targeting, and extreme cryogenic cooling that we're able to catch this vanishingly faint signal coming from the edge of the solar system. And it's exactly this hard-won data that helped explain the anomaly we started with. Why did space seem to thicken as the probes left the solar system behind? Scientists had assumed that crossing into interstellar space would feel like a smooth fade into emptier and emptier surroundings. But the actual boundary of our solar system, known as the heliopause, doesn't work that way. Our sun constantly blasts out a stream of charged particles called the solar wind, which spreads out in every direction and forms a huge protective bubble around the planets, the heliosphere. But the space between the stars isn't truly empty either. It's filled with cold plasma, gas, and dust left over from ancient supernovae. Where the solar wind meets that interstellar material, at the outer edge of the heliosphere, you get a chaotic border zone. Solar wind pushing out from the inside, interstellar plasma pushing in from the outside, and right at that boundary, particle density spikes sharply. As of 2026, both probes have long since punched through that barrier and are now cruising through the cold expanse between the stars. But time is running out for them. Their biggest enemy isn't micrometeorites or radiation. It's simply running out of power. Out where the Voyagers are, the sun is still visible, but only as a bright star, and there's nowhere near enough sunlight left for solar panels to be useful. Instead, both spacecraft run on RTGs, radioisotope thermoelectric generators. Contrary to what a lot of people assume, these aren't tiny nuclear reactors. There's no controlled chain reaction, no complicated electronics, and no moving parts that could wear out over 50 years. The design is elegantly simple. Inside sits a durable capsule of plutonium-238. This isotope naturally decays and continuously produces heat, keeping the capsule very hot. Wrapped tightly around it are thermocouples, plates made from semiconductor material. When one side of a thermocouple touches the scalding hot plutonium capsule and the other side faces the freezing vacuum of space, that temperature difference generates an electric current. But physics doesn't bend for anyone. Plutonium-238 has a half-life of 88 years, meaning it's constantly decaying and putting out less and less heat, while the thermocouples themselves gradually degrade too. So the generators lose power, year after year. Of the original 11 scientific instruments each spacecraft carried, only a handful are still working. Voyager 1 is down to 2, Voyager 2 has 3. To stretch out the probe's lives as long as possible, NASA engineers have been shutting down systems one at a time, making tough calls about which instruments to sacrifice next. Which raises another question. How do the spacecraft even receive these shutdown commands? It works through that same deep space network, just running in reverse. While the probes whisper back to Earth at 20 watts, the 70-meter dishes on the ground send a powerful, tightly focused beam out into space carrying tens of thousands of watts. That signal also weakens badly over the 24 billion kilometer trip, but each Voyager carries its own 3.7-meter dish locked onto Earth with pinpoint precision that gathers up those faint scraps of incoming energy. The connection speed is almost laughably slow, a mere 16 bits per second. A single command package can take hours just to upload. And confirming it actually worked takes nearly 2 full days. It was through exactly this painstaking process that engineers eventually had to send the command to shut off even the heaters protecting the instruments from freezing. To everyone's surprise, this decades-old electronics has kept working even in the bitter cold of deep space. Still, the power keeps draining. Sometime in the next few years, likely by the early 2030s, there simply won't be enough power left to keep even the transmitters running. Engineers will have to send one last command, and then the connection will be gone for good. Here on Earth, there will be total silence. But for the Voyagers themselves, losing contact will just be the start of a much longer, silent journey. Once the transmitters finally go dark, the Voyagers will stop being scientific instruments, but they won't become ordinary space junk either. Bolted to the side of each spacecraft is the now iconic Golden Record, a gold-plated copper disc carrying sounds from Earth, music, photographs, and greetings recorded in dozens of languages. Etched on its cover is a map showing exactly where our planet sits. It's basically a message in a bottle, tossed into the vastness of space, meant for someone we'll almost certainly never meet. Once the signal is lost, their true silent voyage through time really begins. In roughly 300 years, the probes will reach the inner edge of the Oort cloud, that enormous shell of icy bodies surrounding our solar system. It'll take them about 30,000 years just to drift all the way through it before they finally leave the solar system's outer edges behind for good. Around 40,000 years from now, they'll make their first close passes by other stars. By then, micrometeorites will have pitted their outer casings, their antennas will be warped, and radiation will have darkened the metal. But the sturdy aluminum housing should keep the golden records themselves in pristine shape. About 5 billion years from now, our sun will begin dying, swelling into a red giant, and Earth will either be swallowed up or scorched into a lifeless cinder. The Voyagers, though, will be long gone by then. Around that same time, another massive event could be unfolding, the collision of the Milky Way and the Andromeda Galaxy. If that collision really happens, the orbits of billions of stars will get thrown into chaos by gravity, and it's basically impossible to guess where the two tiny Voyagers will end up. Maybe they'll drift on the outer edge of a newly merged galaxy. Or maybe they'll get flung even further out into the emptiness of intergalactic space. Around 10 trillion years from now, even the longest-lived stars in the universe, red dwarfs, will finally burn out, and the universe will fall into permanent darkness. That marks the start of what's sometimes called the era of matter decay, when even the atoms making up the spacecraft's hull and the golden records themselves will begin, very slowly, to break apart. The laws of physics will quite literally start erasing the Voyagers from existence. But until that very last atom finally decays, these two small, battered pieces of 1970s engineering will keep drifting silently through the void. They'll remain among the most enduring things human hands have ever built, lasting proof that somewhere in the universe on a small pale blue dot there was once life that looked up at the sky and dared to reach for the stars.